Good morning, I am Seema. Today we are studying the chapter of the p block elements. In class 11th, you have learned that the p block elements are placed in groups 13 to 18 of the periodic table. Their valence shell electronic configuration is ns1 and p1 to 6 except helium, which has 1s2 configuration. The properties of p block elements, like that of the others, are greatly influenced by the atomic size, ionization enthalpy, electron gain enthalpy, and electronegativity. The absence of the d orbitals in the second period and presence of d or d and f orbitals in heavier elements starting from the third period onwards have significant effects on the properties of the elements. In addition, the presence of all the three types of elements, metals, metalloids, and non-metals, bring diversification in the chemistry of these elements. Having learned that the chemistry of elements of groups 13 and the 14 of the p block of periodic table in class 11th, you will learn the chemistry of the elements of subsequent groups in this unit. Group 15 includes nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, there is a shift from non-metallic to metallic through the metalloidic character. Nitrogen and phosphorus are the non-metals, arsenic and antimony metalloids, and bismuth is a typical metal. Molecular nitrogen compromises the 78% by volume of the atmosphere. In the earth crust, it occurs as sodium nitrate called Kyle sulfate and potassium nitrate. It is found in the form of proteins in plants and animals. Phosphorus occurs in the minerals of the apatite family, which are the main components of the phosphate rocks. Phosphorus is an essential constituent of the animals and the plants matters. It is present in the bones as well as in the living cells. The phosphoproteins are present in milk and eggs. Arsenic, antimony, and bismuth are found mainly as the sulfide minerals. Trends of the sum of the atomic, physical, and the chemical properties of the group are discussed below. First is the electronic configuration. The valence shell electronic configuration of these elements is ns2 np3. The s orbital in these elements is completely filled and p orbitals are half filled, making their electronic configuration extra stable. Second is atomic radii and ionic radii. Covalent and ionic radii increase in the size down the group. There is a considerable increase in covalent radius from nitrogen to phosphorus. However, from arsenic to bismuth, only a small increase in the covalent radius is observed. This is due to the presence of completely filled d and f orbitals in the heavier members. Ionization enthalpy. Ionization enthalpy decreases down the group due to the gradual increase in the atomic size because of the extra stable half-filled p orbitals, electronic configuration, and smaller size. The ionization enthalpy of the group 15 elements is much greater than that of group 14 elements in the corresponding periods. The order of the successive ionization enthalpies accepted is the ionization enthalpies of the one is less than the 2 and the 3. It means ionization enthalpy of the third is greater than the second and then the first. Electron negativity. The electronegativity value in general decreases down the group with increasing the atomic size. However, amongst the heavier elements, the difference is not that much pronounced. Physical properties. All the elements of this group are polyatomic. Dinitrogen is a diatomic gas, while all the others are solids. Metallic character increase down the group. Nitrogen and phosphorus are non-metals. Arsenic and antimony metalloids, and bismuth is a metal. This is due to the decrease in the ionization enthalpy and increase in the atomic size. The boiling points in general increase from top to bottom in the group, but the melting point increases up to arsenic and then decrease up to bismuth. Except nitrogen, all elements shows the allotropy. Chemical properties. The common oxidation states of these elements are -3, +3, and +5. The tendency to exhibit -3 oxidation state decreases down the group due to the increase in the size and metallic character. In fact, last member of the group bismuth hardly forms any compound in -3 oxidation state. The stability of +5 oxidation state decreased down the group. The only well characterized bismuth compound is BiF5. The stability of +5 oxidation state decreases and that of +3 state increases. Nitrogen exhibit +1, +2, +4 oxidation states. Also, when it reacts with oxygen, phosphorus also shows +1 and +4 oxidation state in some oxo acids. In the case of the nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solutions. Similarly, in case of the phosphorus, nearly all the intermediate oxidation states disproportionate into +5 and -3 both in the alkali and acids. However, +3 oxidation state in case of the arsenic, antimony and bismuth becomes the increasingly stable with respect to disproportionation. Nitrogen is restricted to a maximum covalency of 4 since only 4 orbitals are available for bonding. The heavier elements have vacant d orbitals in the outermost shell which can be used for bonding and hence expand their covalence as in F6 negative. Anomalous properties of the nitrogen. Nitrogen differs from the rest of the members of this group due to its small size, high electronegativity, high ionization enthalpy and non-availability of the d orbitals. Nitrogen has unique ability to form the pp multiple bonding with itself and with other elements having the small size and high electronegativity. Heavier elements of this group do not form pp bonds as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. Thus, nitrogen exhibit as a diatomic molecules with a triple bond between the two atoms. Consequently, its bond enthalpy is very high. On the contrary, phosphorus, arsenic and antimony form the single bonds as P single bond P, arsenic single bond arsenic and antimony single bond antimony, while bismuth forms the metallic bonds in the elemental state. However, the single nitrogen-nitrogen bond is then the single phosphorus bond because of the high interelectronic repulsion of the non-bonding electrons owing to the small bond length. As a result of the catenation tendency is weaker in the nitrogen. Another factor which affects the chemistry of the nitrogen is the absence of d orbitals in its valence shell. Besides restricting its covalency to 4, nitrogen cannot form d-pi bond as the heavier elements phosphorus and arsenic can form the d-pi bond also with transition metal when their compounds like phosphorus C2H5 for thrice act as the ligand. Reactivity towards the hydrogen. All the elements of the group 15 form the hydrides of the type EH3 where E is the nitrogen, phosphorus, arsenic and antimony. Some of the properties of these hydrides show the regular graduations in their property. The stability of the hydrides decrease from ammonia to is BiS3 which can be observed from their bond dissociation enthalpy. Consequently, the reducing character of the hydrides increase ammonia is only a mild reducing agent while BiH3 is the strongest reducing agent amongst all the hydrides. The activity towards the oxygen. All these elements forms the two types of oxides. The oxides in the higher oxidation state of the element is more acidic than that of the lower oxidation state. Their acidic character decreased out the group. The oxides of the type O3 of the nitrogen and the phosphorus are purely acidic. That of the arsenic and antimony amphoteric and those of bismuth predominantly basic. Reactivity towards the halogens. These elements react to form the two series of the halides EX3 and EX5. Nitrogen does not form the pentahalides due to the non-availability of the d orbitals in its valence shell. Pentahalides are more covalent than the trihalides. All the trihalides of these elements except those of the nitrogen are stable. In the case of the nitrogen, only NF3 is known to be stable. Trihalides except BiF3 are predominantly covalent in the nature. Reactivity towards the metal. All these elements react with the metals to form their binary compounds exhibiting -3 oxidation state, such as calcium nitride, zinc antimonide, and the magnesium bismuthide. Though nitrogen exhibits +5 oxidation states, it does not form the pentahalides. Give reason: because nitrogen has s and p orbitals only. It does not have the orbital to expand its covalent beyond 4. That's why it does not form the pentahalides. Preparation of dinitrogen. Dinitrogen is produced commercially by the liquefaction and fractional distillation of air. Liquid dinitrogen distills out first, leaving behind the liquid oxygen. In the laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrite. Small amounts of the NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through the aqueous sulfuric acid containing potassium dichromate. It can also be obtained by the thermal decomposition of ammonium dichromate. Very pure nitrogen can be obtained by the thermal decomposition of sodium or the barium azide. Properties. Dinitrogen is a colorless, odorless, tasteless and non-toxic gas. Nitrogen atom has two stable isotopes, nitrogen 14 and nitrogen 15. It has a very low solubility in the water and low freezing and boiling point. Dinitrogen is rather inert at the room temperature because of high bond enthalpy of the nitrogen-nitrogen bond. The activity, however, increases rapidly with rise in the temperature. At higher temperatures, it directly combines with the some metals to form the predominantly ionic nitrides and with non-metals, covalent nitrides. It combines with the hydrogen at about 773 Kelvin in presence of catalyst. Uses. The main use of the dinitrogen in the manufacture of the ammonia and the other industrial chemicals containing nitrogen. It also finds the use where an inert atmosphere is required. Liquid dinitrogen is used as a refrigerant to preserve the biological materials, food items, and in the cryosurgery. Ammonia preparation. Ammonia is a present in the small quantities in air and soil, where it is formed by the decay of nitrogenous organic matter. On a small scale, ammonia is obtained from the ammonium salt, which decomposes when treated with the caustic soda or calcium hydroxide. In accordance with Le Chatelier principle, high pressure would favor the formation of ammonia. The optimum conditions for the production of ammonia are a pressure of 200 into 10 raised to the power 5 pascals and a temperature of nearly 700 Kelvin, and the use of the catalyst such as the iron oxide with small amount of the aluminium trioxides to increase the rate of the attainment of equilibrium. The earlier iron was used as a catalyst with molybdenum as a promoter. Properties. Ammonia is a colorless gas with the pungent odor. Its freezing and the boiling points are 198.4 and 293.7 Kelvin respectively. In the solid and liquid states, it is associated through the hydrogen bonds as in the case of water, and that accounts for its higher melting and boiling points than accepted on the basis of its molecular mass. The ammonia molecule is trigonal pyramidal with the nitrogen atom at the apex. It has 3 bond pairs and 1 lone pair of the electrons. Ammonia gas is highly soluble in water. Its aqueous solution is weakly basic due to the formation of OH negative ions. It forms ammonium salts with the acids. As a weak base, it precipitates the hydroxides of the many metals from their salt solutions. For example, the presence of an lone pair of the electrons on the nitrogen atom of the ammonia molecules make it a Lewis base. It donates the electron pair and forms linkage with metal ions, and the formation of such complex compounds finds the applications in the detection of the metal ions such as Cu2 positives and the Az positive ions. Uses. Ammonia is used to produce the various nitrogenous fertilizers and in the manufacture of the some inorganic nitrogen compounds, the most important one being nitric acid. Liquid ammonia is also used as a refrigerant. Next is Lewis dot. Main resonance structure and bond parameters of the oxides are given in these tables. Preparation. In laboratory, nitric acid is prepared by heating KNO3 or NaNO3 and concentrated H2SO4 in a glass retort. On a large scale, it is prepared mainly by the Ostwald process. This method is based upon catalytic oxidation of the ammonia by atmospheric oxygens. NO thus formed is recycled and the aqueous HNO3 can be concentrated by distillation up to 68% by mass. Further concentration to 98% can be achieved by dehydration with concentrated H2SO4. Properties. It is a colorless liquid. Laboratory grade nitric acid contains nearly 68% of the HNO3 by mass and has a specific gravity. In the gaseous state, HNO3 exists as a planar molecule with the structure. In the aqueous solution, nitric acid behaves as a strong acid giving hydronium and the nitrate ion. Concentrated nitric acid is a strong oxidizing agent and attacks most metals except noble metals such as gold and platinum. The products of the oxidation depends upon the concentration of the acid, temperature and the nature of the material undergoing the oxidation. Zinc reacts with dilute nitric acid to give M2O and with the concentrated acid to give NO2. Some metals do not dissolve in the concentrated nitric acid because of the formation of a passive film of oxides on the surface. Concentrated nitric acid also oxidizes non-metals and their compounds. Iodine is oxidized to iodic acid, carbon to carbon dioxide, sulfur to H2SO4 and phosphorus to phosphoric acids. Brown ring test. The familiar brown ring for the nitrates depends on the ability of the Fe2 positive ions to reduce the nitrates to nitric oxide, which reacts with Fe2 positive ions to form a brown colored complex. The test is usually carried out by adding dilute ferrous sulfate solution to an aqueous solution containing nitrate ion and then carefully adding concentrated sulfuric acid along the sides of the test tube. A brown ring at the interference between the solution and the sulfuric acid layers indicates the presence of nitrate ion in the solution. Uses. The major use of the nitric acid in the manufacture of the ammonium nitrate for fertilizers and the other nitrates for use in the explosives and pyrotechnics. It is also used for the preparation of nitroglycerin, trinitrotoluene and other organic nitro compounds. Other major uses are in pickling of stainless steel, etching of metals and as an oxidizer in the rock fuels. Phosphorus is found in many allotropic forms, the important ones being white, red and black. White phosphorus is a translucent while solids. It is poisonous, insoluble in water but soluble in the carbon disulfides and glows in dark. It dissolves in boiling NaOH solution in an inert atmosphere giving the phosphine. White phosphorus is less stable and therefore more reactive than the other solid phases under normal conditions because of the angularly strain in the P4 molecule where the angles are only 60 degree. It readily catches the fire in air to give the dense white fumes of P4 or 10. It consists of discrete tetrahedral P4 molecule. Red phosphorus is obtained by heating white phosphorus at 573 Kelvin in an inert atmosphere for several days. When red phosphorus is heated under high pressure, a series of phases of black phosphorus is formed. Red phosphorus possesses an iron gray luster. It is odorless, non-poisonous and insoluble in water as well as in carbon disulfide. Chemically, red phosphorus is much less reactive than the white phosphorus. It does not glow in dark. It is polymeric, consisting of chain of P4 tetrahedral linked together in the manner. Black phosphorus has two forms, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus is formed when red phosphorus is heated in a sealed tube at 803 Kelvin. It can be sublimed in air and has an opaque monoclinic or rhombohedral crystals. It does not oxidize in the air. Beta black phosphorus is prepared by heating white phosphorus at 473 Kelvin under high pressure. It does not burn in an air up to 673 Kelvin. Preparation. Phosphine is prepared by the reaction of calcium phosphide with water or dilute HCl. In the laboratory, it is prepared by heating white phosphorus with concentrated NaOH solution in an inert atmosphere. When pure, it is non-inflammable but becomes inflammable owing to the presence of P2H4 or P4 vapors. To purify it from the impurities, it is absorbed in HI to form the phosphonium iodide, which on treating with KOH gives off phosphine properties. It is a colorless gas with rotten fish smell and is highly poisonous. It explodes in contact with traces of oxidizing agents like HNO3, Cl2 and Br2 vapors. It is highly soluble in water. The solution of phosphine in water decomposes in presence of light, giving the red phosphorus and H2. Then absorbed in copper sulfate or mercury chloride solution, the corresponding phosphides are obtained. The spontaneous combustion of phosphine is technically used in Holmes signals. Containers containing the calcium carbide and calcium phosphide are pyrezed and thrown in the sea. When the gases evolve, burn and serve as a signal. It is also used in smoke screens. Phosphorus halides. Phosphorus forms the two types of the halide PX3 and PX5 preparation. It is obtained by passing the dry chlorine over heated white phosphorus. It is also obtained by the action of thionyl chloride with white phosphorus. Properties. It is a colorless oily liquid and hydrolysis in presence of moisture. It reacts with organic compounds containing OH groups such as CH3COH, C2H5. It has pyramidal shape as shown in which phosphorus is sp3 hybridized. Preparation. Phosphorus pentachloride is prepared by the reaction of the white phosphorus with excess of dry chlorine. Properties. PCl5 is a yellowish white powder and in moist air it hydrolyzes to PuCl3 and finally get converted to phosphoric acid. When heated it supplies but decomposes on stronger heating. It reacts with organic compounds containing OH group converting them to chloro derivatives. Finely divided metals on heating with PCl5 gives corresponding chlorides. It is used in the synthesis of some organic compounds. In gaseous and liquid phases, it has a trigonal bipyramidal structure. The three equatorial PCl bonds are equivalent while the two axials are longer than equatorial bonds. This is due to the fact that the axial bonds pairs suffer more repulsion as compared to the equatorial bond pairs. In the solid state, it exists as an ionic solids in which the cation is tetrahedral and the anion is octahedral. Oxoacids of phosphorus. Phosphorus forms a number of oxoacids. The important oxoacids of the phosphorus with their formulas, method of preparation and presence of such characteristic bonds in their structures are given below. The composition of the oxoacids are interrelated in terms of loss or gain of H2O molecules or oxygen atoms. The structures of some important oxoacids are like orthophosphoric acid, pyrophosphoric acid, orthophosphorus acid, polymetaphosphoric acids. In oxoacids, phosphorus is tetrahedrally surrounded by the other atoms. All these acids contain at least one p oxygen bond, phosphorus oxygen bond and one POH bond. The oxoacids in which phosphorus has lower oxidation states contain in addition to P double bond O and POH bonds either phosphorus single bonds or phosphorus hydrogen bonds but not both. These acids in +3 oxidation states of the phosphorus tend to disproportionate to higher and lower oxidation state. For example, orthophosphorus acids on heating disproportionates to orthophosphoric acids. The acids which contain phosphorus hydrogen bond have strong reducing properties. Thus, hypophosphorus acid is a good reducing agent as it contains two phosphorus hydrogen bonds and reduces. These phosphorus hydrogen bonds are not ionizable to give the H positive ions and do not play any role in basicity. Only those hydrogen atoms which are attached with oxygen in phosphorus oxygen bonds form a are ionizable and cause the basicity. Thus, S3PO3 and S3PO4 are dibasic and tribasic respectively as the structure of S3PO3 has 2 POH and S3O4 3. Oxygen, sulfur, selenium, tellurium and polonium are the group of the 16 periodic tables. This is sometimes known as a group of chalcogens. The name is derived from the Greek word for brass and points to association of sulfur and its conjunctions with copper. Most copper minerals contain either oxygen or sulfur and frequently the other members of the group. Occurrence of oxygen is the most abundant of all the elements on the earth. Oxygen forms about 46.6% by mass of the earth's crust. Dry air contains 20.946% oxygen by volume. However, the abundance of the sulfur in the earth crust is only 0.03 to 0.1%. Combined sulfur exists primarily as sulfates such as gypsum. Traces of sulfur occur as hydrogen sulfides in volcanoes. Organic materials such as eggs, proteins, garlic, onion, mustard, hair, and wool contains the sulfur. Selenium and tellurium are also found as the metal selenites and tellurides in sulfide ores. Polonium occurs in nature as a decay product of thorium and uranium materials. The most atomic and physical properties of group 16 along with electronic configuration. Some of the atomic, physical and chemical properties of these trains are discussed below. First is the electronic configuration. The elements of the group 16 have the 6 electrons in the outermost shell and have ns2 np4 general electronic configuration. Atomic and ionic radii. Due to increase in the number of the shells, atomic and ionic radii from top to bottom in the group, the size of the oxygen atom is however exceptionally small. Ionization enthalpy. Ionization enthalpy decreases down the group. It is due to the increase in the size. However, the elements of this group have the lower ionization enthalpy value compared to those of group 15 in the corresponding pairs. This is due to the fact that group 15 elements have extra stable half-filled p orbital electronic configuration. Next property is electron gain enthalpy. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than the sulfur. However, from sulfur onwards, the value again becomes less negative up to polonium. Next property is electronegativity. Next to fluorine, oxygen has the highest electronegativity value amongst the elements. Within the group, electronegativity decreases with an increase in an atomic number. This implies that the metallic character increases from oxygen to polonium. Physical properties. Some of the physical properties of group 16 elements are given in the table. Oxygen and sulfur are no metals. Selenium and tellurium metalloids, whereas polonium is a metal. Polonium is radioactive and is short-lived. All these elements exhibit the allotropy. The melting and boiling point increase with an increase in atomic number down the group. The large difference between the melting and the boiling points of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exhibit as diatomic molecules, whereas sulfur exhibit as polyatomic molecules. Chemical properties. The elements of group 16 exhibit a number of the oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2 except in this case of OF2 where its oxidation state is +2, other elements of the group exhibit the +2, +4, +6 oxidation states but +4, +6 are more common. Sulfur, selenium and tellurium usually shows +4 oxidation states in their compounds with oxygen and +6 with fluorine. The stability of +6 oxidation state decreases down the group and the stability of +4 oxidation state increases. Bonding in +4 and +6 oxidation state is primarily covalent. Anomalous behavior of the oxygen. The anomalous behavior of the oxygen, like other members of p block present in the second pair, is due to its small size and high electronegativity. One typical example of effects of small size and high electronegativity is the presence of strong hydrogen bonding in S2, which is not found in S2s. The absence of d orbitals in oxygen limits its covalency to 4 and in practice rarely exceeds 2 1 and 2. On the other hand, in case of other elements of the group, the valence shells can be explained and the covalence exceeds 4. First is the reactivity with hydrogen. All the elements of group 16 form the hydride of type. Some properties of hydrides are given. Their acidic character increases from H2O to H2Te. The increase in acidic character can be explained in terms of decrease in the bond enthalpy for the dissociation of a bond down the group, owing to the decrease in the enthalpy for the dissociation of Ha bond down the group. The thermal stability of the hydrides also decreased from H2O to H2PO. All the hydrides except the water possess the reducing properties, and this character increased from H2S to H2Te. Reactivity with the oxygen. All these elements forms the oxides of the EO2 and EO3, where E is the sulfur and cerullium, terralium or polonium. Ozone and sulfur dioxide are gases while selenium dioxide is solid. Reducing properties of the dioxide decrease from SO2 to TeO2. SO2 is reducing while TeO2 is an oxidizing agent. Besides EO2 type, sulfur, selenium and tellurium also forms EO3 type oxides. Reactivity towards the halogen. Elements of the group 16 form a large number of halides of type EX6, EX4, EX2, where E is the element of the group and X is the halogen. The stability of the halides decreases in order to fluoride ion greater than chloride ion, then bromide ion, and then iodide ion. Amongst hexahalides, hexafluorides are the only stable halides. All the hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride is exceptionally stable for steric regions. Amongst the tetrafluorides, SF4 is a gas, SAF4 a liquid, and TEF4 a solid. These fluorides have sp3 hybridization and thus have trigonal bipyramidal structure in which one of the equatorial position is occupied by the lower pair of the electrodes. This geometry is also regarded as the Sisa geometry. All the elements except the oxygen forms the dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known metanohalides are dimeric in the nature. These dimeric halides undergo the disproportions and gives to the SeCl2 and reacts and to gives SeCl4 plus 3 selenium. Dioxygen preparation. Dioxygen can be obtained in the laboratory by the following ways: by heating the oxygen containing the salts such as the chlorates, nitrates, and permanganates, by the thermal decomposition of the oxides of the metals low in the electrochemical series and higher oxides of some metals. Hydrogen peroxide is readily decomposed into water and dioxygen by catalysts such as finely divided metals and manganese dioxide. On large scale, it can be prepared from water or air. Electrolysis of the water leads to release of hydrogen at cathode and oxygen at the anode. Industrially, dioxygen is obtained from air by first removing the carbon dioxide and water vapors, and then the remaining gases are liquefied and fractionally distilled to give dinitrogen and dioxygen properties. Dioxygen is a colorless and odorless gas. Its solubility in water is to the extent of 3.08 cm cubic in 100 cm cubic water at 293 Kelvin, which is just sufficient for the vital support for marine and aquatic life. It liquefies at 90 Kelvin and the freezes at 55 Kelvin. Oxygen atom has three stable isotopes: oxygen 16, oxygen 17, and oxygen 80. Molecular oxygen is unique in being paramagnetic in spite of having even number of electrons. Dioxygen directly reacts with nearly all the metals and non-metals except some metals and some noble gases. Its combinations with other elements is often strongly exothermic, which helps in sustaining the reactions. However, to initiate the reaction, some external heating is required as the bond dissociation enthalpy of the oxygen-oxygen double bonds. Some of the reactions of the dioxygen with metals, non-metals, and other compounds are given, like when the calcium reacts with oxygens and to give rise to the calcium oxides. Uses: in addition to its importance, it normal respiration and combustion process. Oxygen is used in oxyacetylene welding in the manufacture of many metals, particularly steel. Oxygen cylinders are widely used in hospitals, high altitude flying, and in mountaineering. The combustion of fuels, example hydrogens in liquid oxygen, provides the tremendous thrust in the rockets. In text question is which of the following does not react with oxygen directly? Zinc, titanium, platinum, or iron. And next is complete the reactions when methane reacts with the oxygens and aluminium reacts with the oxygen. Simple oxides. A binary compound of the oxygens with another element is called oxides. As already stated, oxygen reacts with most of the elements of the periodic table to form the oxides. In many cases, one element forms two or more the oxides. The oxides vary widely in their nature and properties. Oxides can be simple or the mixed. Simple oxides can be classified on the basis of their acidic, basic, or amphoteric character. An oxides that combines with water to give an acid is termed as acidic oxides. For example, when SO2 combines with water to give the H2SO3, an acid. As a general rule, only non-metal oxides are acidic, but oxides of some metals in high oxidation state also have acidic character. The oxides which give a base with water are known as basic oxides. For example, calcium oxides combines with water to give calcium hydroxide. In general, metallic oxides are basic. Some metallic oxides exhibit a dual behavior. They show characteristics of both acidic as well as basic oxides. Such oxides are known as amphoteric oxides. They react with acids as well as alkalines. For example, Al2O3 reacts with acids as well as alkalis. There are more oxides which are neither acidic nor basic. Such oxides are known as neutral oxides. Examples of neutral oxides are CO, NO, and N2O. Ozone is an allotropic form of oxygen. It is too reactive to remain for long in the atmosphere at sea level. At a height of about 20 kilometers, it is formed from atmospheric oxygen in presence of sunlight. This ozone layer protects the Earth's surface from excessive concentration of ultraviolet radiations. Preparation. When a slow dry stream of oxygen is passed through a silent electrical discharge, conversion of oxygen to ozone 10% occurs. The product is known as ozonized oxygen. Since the formation of ozone from oxygen is an endothermic process, it is necessary to use a silent electrical discharge in its preparation to prevent its decomposition. If concentrations of the ozone greater than 10% are required, a battery of ozonists can be used, and the pure ozone can be condensed in a vessel surrounded by liquid oxygen. Properties. Pure ozone is a pale blue gas, dark blue liquid, and violet black solids. Ozone has a characteristic smell and its small concentration. It is harmless. However, if the concentration rises above 100 parts per million, breathing becomes uncomfortable, resulting in heart attack and nausea. Ozone is thermodynamically unstable with respect to oxygen, since its decomposition into the oxygen results into the liberation of the heat and an increase in the entropy. These two effects reinforce each other, resulting in large negative gives free energy changes for its conversions into oxygen. It is not really surprising, therefore, high concentration of ozone can be dangerously explosive due to the case with which it liberates the atoms of the nascent oxygens. It acts as a powerful oxidizing agent. For example, it oxidizes lead sulfide to the lead sulfate and iodide ions to iodine. When ozone reacts with an excess of potassium iodide solution buffered with a borate buffer, iodine is liberated, which can be titrated against a standard solution of sodium thiosulfate. This is a quantitative method for estimating oxygen gas. Experiments have shown that nitrogen oxides very rapidly with ozone, and there is thus the possibility that the nitrogen oxides emitted from the exhaust systems of supersonic jet aeroplanes might be slowly depleting the concentration of the ozone layer in the upper atmosphere. Another threat to this ozone layer is probably possessed by the use of the freons which are used in aerosol sprays and as refrigerants. The two oxygen bonds length in the ozone molecule are identical and the molecule is angular as accepted with a bond angle of about 117 degrees Celsius. It is a resonance hybrid of two main forms uses. It is used as a germicide, disinfectant, and for sterilizing water. It is also used for bleaching oils, ivory, flour, starch. It acts as an oxidizing agent in the manufacture of potassium permanganate. Sulfur allotropic forms. Sulfur forms the numerous allotropes of which the yellow rhombic alpha sulfur, alpha sulfur and monoclinic beta sulfur forms are the most important. The stable form at room temperature is rhombic sulfur, which transforms to monoclinic sulfur when heated above 369 Kelvin. Rhombic sulfur. This allotrope is yellow in color and specific gravity. Rhombic sulfur crystals are formed on evaporating the solution of rolled sulfur in CS2. It is insoluble in water but dissolves to some extent in benzene, alcohol, and ether. It is rarely soluble in CS2. Monoclinic sulfur. Its melting point is 393 Kelvin and specific gravity 1.98. It is soluble in CS2. This form of sulfur is prepared by melting rhombic sulfur in a dish and cooling till crust is formed. Two holes are made in the crust and the remaining liquid pours out. On removing the crust, colorless, needle-shaped crystals of beta sulfur are formed. It is stable above 369 Kelvin and transforms into alpha sulfur below it. Conversely, alpha sulfur is stable below 369 Kelvin and transforms into beta sulfur. Above this at 369 Kelvin, both the forms are stable. This temperature is called transition temperature. Both rhombic and monoclinic sulfur have S8 molecules. These S8 molecules are packed to give different crystal structures. The S8 ring in both the bombs is puckered and has a crown shape. The molecular dimensions. Several other modifications of the sulfur containing 6 to 20 sulfur atoms per ring have been synthesized in the last 2 decades. In cyclo-S6, the ring adopts the chair form and the molecular dimensions are at elevated temperatures, nearly 10,000 Kelvin, S2 is dominant species and is paramagnetic like the O2. Which form of the sulfur shows paramagnetic behavior? This is the example solutions in the vapor state sulfur partially exists as the s2 molecules which has the two unpaired electrons in the anti-bonding orbitals like O2 and hence exhibits the paramagnetism. Sulfur dioxides preparation. Sulfur dioxides is prepared together with a little sulfur trioxides when sulfur is burnt in air or oxygen. In the laboratory, it is readily generated by treating a sulfide with dilute sulfuric acid. Industrially, it is produced as a byproduct of roasting of sulfide ores. The gas after drying is liquefied under pressure and stored in steel cylinders. Properties. Sulfur dioxide is a colorless gas with pungent smell and is highly soluble in water. It liquefies at room temperature under a pressure of 2 atmospheres and boils at 263 Kelvin. Sulfur dioxide, when passed through the water, forms a solution of sulfurous acids. It reacts readily with sodium hydroxide solutions, forming the sodium sulfide, which then reacts with the more sulfur dioxide to form the sodium hydrogen sulfides. In its reactions with water and alkalis, the behavior of sulfur dioxide is very similar to that of the carbon dioxide. Sulfur dioxide reacts with chlorine in presence of charcoal to give sulfur chloride. It is oxidized to sulfur trioxide by oxygen in presence of vanadium oxide catalyst. When moist sulfur dioxide behaves as a reducing agent, for example, it converts iron third into iron second ions and decolorizes acidified potassium permanganate solution. The later reaction is convenient test for the gas. Uses sulfur dioxide is used as in refining petroleum and sugar, second in bleaching wool and silk, and third as an anti-color disinfectant and preservative. Sulfuric acid, sodium hydrogen sulfide and calcium hydrogen sulfides are manufactured from sulfur dioxide. Liquid sulfur dioxide is used as a solvent to dissolve a number of organic and inorganic chemicals. Oxoacids of the sulfur. Sulfur forms a number of oxoacids such as H2SO3, H2S2, H2S2O4, H2S2O5. Some of these acids are unstable and cannot be isolated. They are known in aqueous solution or in the form of their salts. Structures of some important oxoacids. Sulfuric acids manufactures. Sulfuric acid is the one of the most important industrial chemicals worldwide. Sulfuric acid is manufactured by the contact process, which involves the three steps: burning of the sulfur or the sulfide ores in air to generate the sulfur dioxide, conversion of the sulfur dioxide to sulfur trioxide by the reaction with oxygen in presence of a catalyst, and absorption of sulfur trioxide in H2SO4 to give the oil of sulfuric acid is shown in the impurities. The sulfur dioxide produced is purified by removing the dust and other impurities such as arsenic compounds. The key step in manufacture of H2SO4 is the catalytic oxidation of SO2 with O2 to give the sulfur trioxide in presence of V2O5. The reaction is exothermic, reversible, and the forward reactions leads to a decrease in the volume. Therefore, low temperature and high pressure are the favorable conditions for the maximum yield, but the temperature should not be very low, otherwise rate of reactions will become slow. In practice, the plant is operated at a pressure of 2 bar and its temperature of 720 Kelvin. The sulfur trioxide gas from the catalytic converters is absorbed in the concentrated H2SO4 to produce the oleum. Dilution of the oleum with water gives H2SO4 of desired concentrations. In the industrial, two steps are carried out simultaneously to make the process a continuous one and also to reduce the cost. The sulfuric acid obtained by contact process is 96 to 98% pure. Properties: sulfuric acid is a colorless, dense, oily liquid with a specific gravity of 1.84 at 298 Kelvin. The acid freezes at 283 Kelvin and boils at 611 Kelvin. It dissolves in water with evolution of a large quantity of heat. Hence, care must be taken while preparing sulfuric acid solution from concentrated sulfuric acid. The concentrated acid must be added slowly into the water with constant stirring. The chemical reactions of sulfuric acids are as a result of following characteristics: low volatility, strong acidic character, strong affinity for water, and ability to act as a oxidizing agent. In the aqueous solution, sulfuric acid ionizes into two steps. The larger value of K1 greater than the 10 means that H2SO4 is largely dissociated into H positive ions and HSO4 negative. Greater the value of the dissociation constant, the stronger is the acid. The acid forms two series of salts, normal sulfates such as sodium sulfate and copper sulfate, and acid sulfate. Sulfuric acid, because of its low volatility, can be used to manufacture more volatile acids from their corresponding salts. Concentrated sulfuric acid is a strong dehydrating agent. Many VCAT. The gases can be dried by passing them through sulfuric acid, provided the gas do not react with the acids. Sulfuric acid removes the water from the organic compounds. It is evident by its chairing action on carbohydrates. Hot concentrated sulfuric acid is a moderately strong oxidizing agent. In this respect, it is intermediate between phosphoric and nitric acid. Both metals and non-metals are oxidized by concentrated sulfuric acid, which is reduced to SO2. Uses: sulfuric acid is a very important industrial chemical in nation's industrial strength can be judged by the quantity of the sulfuric acid it produces and consumes. It is needed for the manufactures of the hundreds of the other compounds and also in many industrial processes. The bulk of the sulfuric acid produced is used in the manufacture of the fertilizers. Other uses are in the petroleum refining, manufacture of pigments, paints, and the dyestuffs, intermediates, detergent industries, metallurgical applications, cleaning metal before enameling, electroplating, and galvanizing, storage batteries in the manufacture of the nitrocellulose products, and as a laboratory reagents. Next is the group of the 17 elements. Fluorine, chlorine, bromine, iodine, and acetylene are the members of the group 17. These are collectively known as the halogens. Halo means salt and gens means bone. The halogens are highly reactive non-metallic elements like group 1 and group 2. The elements of the group 17 shows the greater similarity amongst themselves. That much similarity is not found in the elements of the other groups of the periodic table. Also, there is the regular graduation in their physical and chemical properties. Acetylene is a radioactive element's occurrence. Fluorine and chlorine are fairly abundant, while bromine and iodine less so. Fluorine is present mainly as insoluble fluorides and the small quantities are present in the soil, river, water, plants and bones and teeth of the animals. Seawater contains chlorides, bromides and iodides of the sodium, potassium, magnesium and calcium, but it is mainly the sodium chloride solutions. The deposit of the dried up seas contains these compounds, example sodium chloride and carnallite. Certain forms of the marine life contains the iodine in their systems. Various seaweeds, for example, contain up to 0.5% of iodine, and child saltpeter contains up to 0.2% of sodium iodide. The important atomic and physical properties of group 17 are explained as: first properties is the electronic configuration. All these elements have 7 electrons in their outermost shell, which is the one electron short of the next noble gas. Atomic number and ionic radii. The halogens have the smallest atomic radii in their respective pairs due to the maximum effective nuclear charge. The atomic radius of the fluorine, like the other elements of the second pair, is extremely small. Atomic and the ionic radii increase from fluorine to iodine due to increasing the number of quantum shells. Ionization enthalpy. They have little tendency to lose the electron, thus they have the very high ionization enthalpy due to the increase in the atomic size. Ionization enthalpy decreases down the group. Electron gain enthalpy. Halogens have maximum negative electron gain enthalpy in the corresponding pairs. This is due to the fact that the atoms of these elements have only one electron less than the stable noble gas configurations. Electron gain enthalpy of the elements of the group becomes the less negative down the group. However, the negative electron gain enthalpy of the fluorine is less than that of the chlorine. It is due to the small size of fluorine atom. As a result, there are strong interelectronic repulsions in the relatively small 2p orbitals of fluorine, and thus the incoming electrons does not experience much attractions. Electronegativity. They have the very high electronegativity. The electronegativity decrease down the group. Fluorine is the most electronegative elements in the periodic table. Next is the physical properties. Halogens displays the smooth variations in their physical properties. Fluorine and chlorine are gaseous, bromine is a liquid, and iodine is a solid. Their melting and boiling points steadily increase with atomic number. All halogens are colored. This is due to the absorption of radiations in absorptions of the radiations in visible regions, which results in the excitation of outer electrons to higher energies level. By absorbing different quanta of radiations, they displace different colors. For example, F2 has yellow chlorine greenish yellow, bromine is red, and iodine is violet color. Fluorine and chlorine reacts with water. Bromine and iodine are only sparingly soluble in water, but are soluble in the various organic solvents such as chloroform, carbon tetrachloride, carbon disulfide, and hydrocarbons to give the colored solutions. One curious anomaly, we notice that the smaller the enthalpy of the dissociation of fluorine compared to that of fluorine, where XX bond dissociation enthalpy from chlorine towards onwards shows the expected trend. Chlorine is greater than the bromine greater than the iodine. A reason for this anomaly is relatively large electron repulsion among the lone pair in the F2 molecule, where they are much closer to each other than in the fluorine. Example is the although the electron gain enthalpy of fluorine is less negative as compared to the chlorine. Fluorine is a stronger oxidizing agent than chlorine 5. It is due to the low enthalpy of the dissociation of fluorine-fluorine bond, high hydration enthalpy of the fluoride ion. Chemical properties. All the halogen exhibit -1 oxidation state. However, chlorine, bromine, and the iodine exhibits the +1, +3, +5, +7 oxidation states. The higher the oxidation states of the chlorine, bromine, and the iodine are released when the halogens are in the combination with the small and the highly electronegative fluorine and the oxygen atoms. Example in interhalogens, oxides and oxoacids. The oxidation state of +4 and +6 occur in the oxides and the oxoacids of the chlorine and bromine. The fluorine atom has no d orbitals and its valence shell has and therefore cannot expand its octet. Being the most electronegative, it exhibits only -1 oxidation state. All the halogens are highly reactive. They react with the metals and non-metals to form the halides. The reactivity of the halogens decreases down the group. The ready acceptance of an electron is the reason for the strong oxidizing nature of the halogens. Fluorine is the strongest oxidizing halogen and its oxidized other halides ions in the solution or even in the solid phase. In general, a halogen oxidizes the halide ions of the higher atomic number. The decreasing oxidizing ability of the halogens in the aqueous solution down the group is evident from their standard electron potential, which are dependent on the parameters. The relative oxidizing power of halogens can further be illustrated by their reactions with the water. Fluorine oxidizes the water to oxygen, whereas chlorine and bromine react with water to form the corresponding hydrohallic and hypophallus acids. The reaction of iodine with water is non-spontaneous. In fact, iodide ion can be oxidized by the oxygen in acidic medium, just the reverse of the reaction observed with fluorine. Anomalous behavior of the fluorine. Like other elements of p block present in the second period of the periodic table, fluorine is anomalous in many properties. For example, ionization enthalpy, electronegativity, and electrode potential are all for the chlorine then accepted from the trend set by the other halogens. Also, ionic and covalent radii, melting point, boiling point, enthalpy of bond dissociation, and electron gain enthalpy are quite lower than the expected. The anomalous behavior of the fluorine is due to its smaller size, highest electronegativity, low fluorine-fluorine bond dissociation enthalpy, and non-availability of the d orbital. Most of the reaction of the fluorine are exothermic. It forms only one oxoacids while the other halogen form a number of oxoacids. Reactivity towards the hydrogen. They also react with the hydrogen to give the hydrogen halides, but affinity for the hydrogen decrease from the fluorine to iodine. Hydrogen halides dissolve in the water to form the hydrohallic acid. Some of the properties of the hydrogen halides are the acidic strength of these acids varies in the order is the hydrogen iodide is greater than the HBr greater than HCl than HF. The stability of this halide decreases down the group due to the decrease in the bond dissociation enthalpy. Second is the reactivity towards the oxygen. Halogens forms many oxides with oxygen, but most of them are unstable. Fluorine forms two oxides, OF2 and O2F2. However, only OF2 is negative, is thermally stable at 298 Kelvin. Are essential oxygen fluorides because of the higher electronegativity of the fluorine than the oxygen. Both are strong fluorinating agents. O2F2 oxides plutonium 2 and the reaction is removing the plutonium as the PuF6 from the spent nuclear fuel. Chlorine, bromine, and iodine form the oxides in which the oxidation states of these halogens range from +1 to +7. A combination of the kinetic and thermodynamic factor lead to the generally decreasing order of stability of oxides formed by the halogens. The higher oxides of halogens tends to be more stable than the lower ones. Chlorine oxides are highly reactive oxidizing agent and tend to explode. The bromine oxides are the least stable halogen oxides and exist only at the lower temperature. The iodine oxides are insoluble solids and decompose on heating. Reactivity towards the metals. Halogens reacts with metals to form metal halides. The ionic character of the halides decrease in the order if a metal exhibits more than the one oxidation state, the halides in the higher oxidation states will be more covalent than the one in the lower oxidation states. Next example is the fluorine exhibits only -1 oxidation state, whereas other halogens exhibit +1, +3, 5 or +7 oxidation states. Why? Fluorine is the most electronegative elements and cannot exhibit any positive oxidation state. Other halogens have d orbitals and therefore can expand their octets and show +1, +3, +5 oxidation states. Chlor- Chlorine was discovered in 1774 by the scale by the action of the HCl on MnO2. In 1810, Davy established its elementary nature and suggested the name chlorine on account of its color. Preparation. It can be prepared by the one of the following method: by heating manganese dioxides with concentrated hydrochloric acid. Second is the by the action of the HCl on potassium permanganate. Manufacture of the chlorine. Dickens process by the oxidation of the hydrogen chlorine gas by the atmosphere oxygen in the presence of CuCl2. Electrolytic process. Chlorine is obtained by the electrolysis of brine. Chlorine is liberated at the anode. It is also obtained as a byproduct in many chemical industries. Properties. It is a greenish yellow gas with pungent and suffocating odor. It is about 2 to 5 times heavier than air. It can be liquefied easily into the greenish yellow liquid which boils at 239 Kelvin. It is soluble in the water. With excess ammonia, chlorine gives nitrogen and ammonium chloride, whereas the excess chlorine, nitrogen trichloride is formed. With cold and dilute alkalis, chlorine produces a mixture of chloride and hypochlorite, but with hot and concentrated alkalis, it gives the chloride and chlorate. The next is the composition of the bleaching powder is calcium oxychloride. Chlorine reacts with hydrocarbons and gives substitution products with saturated hydrocarbons and addition products with unsaturated hydrocarbons. Chlorine water on standing loses its yellow color due to the formation of HCl and HOCl. Hypochlorous acid so formed gives the nascent oxygen which is responsible for oxidizing and the bleaching. It oxides the ferrous to ferric and sulfide to sulfate. Chlorine oxides the sulfur dioxide to sulfur trioxides and iodine to iodide. In the presence of the water, they form sulfuric acids and iodic acid respectively. Uses. It is used for the bleaching wood pulp required for the manufacture of paper and iron, bleaching powder in the textiles, in the extraction of the gold and the platinum, in the manufacture of dyes, drugs, organic compounds such as CCl4, CHCl3, DDT, refrigerants, in sterilizing drinking water and the preparation of poisonous gases such as the phosphogen, tear gases, mustard gas. Hydrogen chloride. It bleaches the vegetable or the organic matter in the presence of the moisture. Bleaching effect of chlorine is permanent. Glover prepared this acid in 1648 by heating the common salt with concentrated sulfuric acid. Davy in 1810 showed that is a compound of hydrogen and chlorine. Preparation in the laboratory. It is prepared by heating sodium chloride with concentrated sulfuric acid. HCl can also be dried by passing through concentrated sulfur acid. Properties. It is a colorless and pungent smelling gas. It is easily liquefied to a colorless liquids and freezes to a white crystalline solids. Its aqueous solution is called hydrochloric acid. High value of dissociation constant indicates that it is a strong acid in water. It reacts with NH3 and gives white fumes. When 3 parts of concentrated HCl and 1 part of concentrated HNO3 are mixed. Aquaresia is formed, which is used for dissolving the noble gases. Uses: it is used in the manufacture of the chlorine NH4Cl glucose for the extracting glue from bones and purifying the bone plaque. Also used in the medicine and as a laboratory reagent. Oxoacids of the halogen, due to the high electronegativity and the small size, fluorine forms the only the one oxoacids, HOF, known as fluoric acid or hypofluorous acid. The other halogen forms the several oxoacids. Most of them cannot be isolated in pure state. They are stable only in aqueous solutions or in the form of their salts. Interhalogens compounds: when the two different halogens reacts with each other, interhalogen compounds are formed. These can be assigned general composition as XX, XX3, XX5, XX7, and X is the halogens of the larger size and X the smaller size. X is more electropositive than X dash. As the ratio between the radii of the X and X dash increases, the number of the atoms per molecule also increases. Thus, iodine fluoride should have the maximum number of the atoms, as the ratio of the radii between iodine and fluorine should be the maximum. Preparation: the interhalogen compounds can be prepared by the direct combination or by the action of halogen or lower interhalogen compounds. The product form depends upon the some specific conditions. Properties: some properties are: these are all covalent molecules and are diamagnetic in nature. They are volatile solids or liquids at 298 Kelvin except CIF, which is a gas. Their physical properties are intermediate between those of the constituent halogens except that their melting and boiling point. Their chemical reactions can be compared with individual halogens. In general, interhalogen compounds are more reactive than the halogen. This is because XX bond in the interhalogens is weaker than the XX bond in the halogens except fluorine-fluorine bond. All these undergo the hydrolysis gives the light ion derived from the smaller halogens and hypohalite halide. Their molecular structures are very interesting, which can be explained on the basis of the Vesper theory. The XX3 compounds have the bent T-shape, XX5 compounds scale pyramidal, and IF7 has the pentagonal bipyramidal structures. Group 18 elements. Group 18 consists of 6 elements: helium, neon, argon, krypton, xenon, and radon. All these are gases and chemically unreactive. They form very compounds. Because of these, they are termed noble gases. Occurrence: all the noble gases except the radon occur in the atmospheres. Their atmospheric abundance in the dry air is 1%, by the volume of which argon is the major constituent. Helium and sometimes neon are found in minerals of radioactive origin. Example: pitchblende, monazite, cleveite. The main commercial source of helium is the natural gas. Xenon and radon are the rarest elements of the group. Radon is obtained as a decay product of the radium. Some physical properties of the group 18th element is the electronic configurations. All the noble gases have the general electronic configuration is ns2np6 except the helium, which has one s2. Many of the properties of noble gases, including their inactive nature, are ascribed to their closed cell structures. Ionization enthalpy: due to the stable electronic configurations, these gases exhibit very high ionization enthalpy. However, it decreases down the group with increase in atomic size. Atomic radii increase down the group with increase in atomic number. Electron gain enthalpy: since noble gases have stable electronic configurations, they have no tendency to accept the electron and therefore have large positive values of electron gain enthalpy. Physical properties: all the noble gases are monoatomic. They are colorless, odorless, and tasteless. They are sparingly soluble in water. They have very low melting and boiling points because the only one type of the interatomic interaction in these elements is weak dispersion force. Helium has the lowest boiling point and none of any known substance. It has unusual property of diffusion through most commonly used laboratory materials such as rubber, glass, and plastic. Question is: the noble gases have very low boiling point. Why? because noble gases being monoatomic have no interatomic forces except the weak dispersion forces, and therefore they are liquefied at very low temperatures, hence they have the low boiling point. Chemical properties. In general, noble gases are least reactive. Their inertness to chemical reactivity is attributed to the following reasons. The noble gases, except the helium, have completely failed ns2 and p6 electronic configuration in their valence shell. They have high ionization enthalpy and more positive electron gain enthalpy. The reactivity of the noble gases has been investigated occasionally ever since their discovery, but all attempts to force them to react to form the compounds were unsuccessful for quite a few years. In March 1960, Neil Bartlett, then a University of the British Columbia, observed the reaction of a noble gas. First, he prepared a red compound which is formulated as O2 positive PtF6 negative. He then realized that the first ionization enthalpy of molecular oxygen was almost identical with that of xenon. He made efforts to prepare same type of compound with Xc and was successful in predicting the another red color compound. After this discovery, a number of the xenon compound is mainly with most electronegative elements like fluorine, oxygen have been synthesized. The compound of krypton are favor only the difluoride has been studied in detail. Compound of the radon have not been isolated but only identified by radio tracker technique. No true compound of argon, neon or helium are yet known. Xenon fluorine compounds. Xenon forms the three binary fluorides XeF2, XeF4, XeF6 by the direct reaction of elements under appropriate experimental conditions. XeF6 can also be prepared by the interactions of the Xe4 and O2 F2. XeF2, XeF4 and F6 are colorless crystalline solids and sublime rapidly at 298 Kelvin. They are more powerful fluorinating agents. These are readily hydrolyzed even by traces of water. For example, XeF2 is hydrolyzed to give Xe. The structure of three xenon fluorides can be deduced from VSEPR, and these are shown have linear and square planar structures respectively. XeF6 has the 7 electron pairs, bonding pairs and 1 lone pairs, would thus have a distorted octahedral structures as found experimentally in the gas phase. Xenon fluorides reacts with fluoride ion attempting acceptors to form the cationic species and fluoride ion donors to form the fluoroanions. Xenon oxygen compounds. Hydrolysis of XeF4 and F6 with water gives rise to XeO3. Partial hydrolysis of XeF6 gives the oxyfluorides. XeO3 is a colorless explosive solid and has a pyramidal molecular structures. XeOF4 is a colorless volatile liquid and has a square pyramidal molecular uses. Helium is a non-inflammable and light gas, hence it is used in filling the balloons for the meteorological observations. It is also used in the gas-colored nuclear reactor. Liquid helium binds use a cryogenic agent for carrying out various experiments at the lower temperature. It is used to produce and sustain the powerful superconducting magnets which forms an essential part of the modern NMR spectrometers regions and the magnetic resonance imaging system for the clinical diagnosis. It is used as a diluent for the oxygen in modern diving apparatus because of its very low solubility in blood. Neon is used in discharge tubes and fluorescent bulbs for advertisement displays purposes. Neon bulbs are used in botanical gardens and in greenhouses. Argon is used mainly to provide an inert atmosphere in high temperature metallurgical process and for filling the electric bulbs. It is also used in the laboratory for handling the substances that are air sensitive. There are no significant uses of xenon and krypton. They are used in light bulbs designed for the special purposes. So all this about the p-block elements. Thank you.